depending on where you want to go with it, that mediates forces between dark matter particles, but also mixes with the standard model somehow, so we have some access to it. So you could paint a nice little picture here that all these things are tied together, but the details are difficult to reconcile, actually. Okay, so someone mentioned to me yesterday that they'd like to know a little more about what we know about dark matter and what we assume about dark matter. I don't want to spend too much time on this because you've all seen dark matter talks before, but the only thing we really know is that it exerts gravitational forces. We don't know it's a WIMP, we don't know it's an accent, we don't know mass range to within 30 orders of magnitude. I mean, we don't actually know much. We assume a lot, we try things, we don't know very much. We do know that galaxies in nearby clusters move too fast. We've known that for several decades. We know that spiral galaxies have flat rotation curves, so if you plot the velocity as a function of distance from the center of the galaxy, it's much flatter than it should be. That's been known for my whole life. There are these beautiful examples of lensing clusters where you get these strong lensing arcs, and we know general relativity, we know how light bends, we can estimate the mass inside of that ring, and it's a factor of several bigger than you get by adding up all the light for any reasonable assumptions at all about mass to light ratios. An amusing aside here, when Hubble first came out with this image of Abell 2218, so I was a grad student at Berkeley back in the day, and High Spinrad was one of the grand old astronomers. And he said, "Oh, that looks familiar." And he pulled a glass plate out he'd taken like 20 years before, a photographic plate, and it had these streaks on it. He said, "I thought there was something wrong with the emulsion." So these things could have been seen decades earlier, but it's very hard to find what you aren't looking for, which is part of the moral of this story. When it comes to theorists who actually work out structure formation, so what's the power spectrum of the distribution of matter on the largest scales, you can try to simulate things like that with no dark matter, and you get results that look horrendously different from what we see in the real universe. And then, of course, the microwave background. The way my colleague Daniel Eisenstein likes to describe this is, you're a kid who gets a present, the first thing you do is shake the box. You see the response to oscillations, and we didn't have to kick the universe, the Big Bang gave it a kick, and there were acoustic oscillations set up in the photon-barren plasma, and then when the universe becomes neutral, those photons just keep going until we see them today. And by the power spectrum of this pattern, we can determine a great deal about the response of the universe to kicks. And one of the things it tells us is that 83% of the matter, plus or minus something small, 83% of the matter does not couple to photons or baryons at that time, meaning at that energy scale. So, okay. So now, those are various ways we know about dark matter, but what is it? So the thing everyone likes to talk about is WIMPs. And that's partly compelling because of this thermal freeze-out argument. I mean, I don't know. We have no evidence that WIMPs exist after decades of looking for them, so, don't attribute too much significance to this. But at least if it's a thermal relic of the Big Bang, you don't have to explain where it came from. Everything's created and annihilated when the temperature of the universe is high, temperature drops, annihilations win, the density drops. And then when the annihilation timescale becomes the age of the universe, particles can't find each other. So annihilation more or less turns off. And then you're left with some relic density of this process. And for very reasonable assumptions about particles in the 100 GeV mass range, you get the right density to be dark matter. So that's a nice argument. Peter Fisher always likes to point out that if you made a similar argument about abundances of other particles in the universe, you're often off by a couple orders of magnitude. So you should always take arguments like this as being fuzzy at the factor of 100 level. But it gives you some place to look. Now, when people start talking about WIMP self-interactions, it might sound like you're going out on a limb. I'm going to be John Doyle here and say I'm still firmly holding on to the tree trunk, because in general, WIMPs have self-interactions. It's actually the general case. To turn it off, you need a conspiracy. So WIMPs have to couple to the Standard Model somehow. They're a thermal relic of the Big Bang. They can couple by Higgs exchange, Z exchange, various things. A lot of these have been, ruled out for all reasonable parts of parameter space, like Z exchange just doesn't seem to work. Or if they go to fermions somehow, if they annihilate to fermions directly or indirectly, you can build Feynman diagrams with loops that go through fermion loops and allow the WIMPs to scatter off each other. Now the cross-section for scattering might be so tiny that it's never relevant, but it's not zero. If the thing's coupled to the Standard Model at all to be created as a thermal relic, this cross-section is not zero unless you have some kind of conspiracy to miraculously cancel things, which you can do. But that's an important thing to keep in mind, right? Self-interaction is actually the generic case, and it's just a question of what is the cross-section. So we have limits on this. This is a commonly shown image of the bullet cluster. Blue is dark matter derived from weak lensing of background objects. Red is the X-ray gas. Galaxies are galaxies. And the idea here is that these clusters went through each other at high speed, a couple thousand kilometers a second. The dark matter in the galaxies coast right through, and the gas lags behind because it got shocked. Yes, sir?
So I'd heard something about, some other similar clusters that didn't quite agree with this picture, and I guess my question was, if you get a limit from the bullet cluster, how does that correspond to studies from other clusters? Are they all consistent now as a story, or is there's some inconsistencies?
Yeah, so Will Dawson has looked at least a dozen clusters, and with all the relevant data, like this one, and he's worked very hard to get the data. This is not an easy thing to do. And some look like this, and some don't. So, yeah, that makes you wonder. In fact, in one case, he found weak evidence, I don't know, 3 sigma or something, that the dark matter was actually lagging behind also. But if you look at enough galaxies, the chance of finding one that's 3 sigma is not small. So, no convincing evidence either way, but I think, ideally you would look at 100 of these and get exquisitely good data, and when the W1st satellite launches someday, it'll do the weak lensing stuff extremely well on these. I mean, it'll just be shooting fish in a barrel. So we should be able to do better on this in the future. But yeah, you're right to be somewhat skeptical. Okay, I mean, but there are some really easy limits from the fact that dark matter halos don't just collapse. Okay, so the kinds of limits you get from these things are of order 0.1 to 1 square centimeter per gram. So we're phrasing that way, so not cross-section per particle. We don't know what the particles are, we don't know the mass, but we can talk about cross-section per gram with these limits. That's not very small, right? If you think about a Thomson cross-section and Avogadro's number and whatever, it would be nice to push that down by orders of magnitude. But still, so, because this is still a fairly big number, there's a lot of room for interesting effects in astrophysics from self-interaction.
Sorry to ask you. So is this very specific to the WIMP, or could you make the same kind of claim for Axion?
Yeah, no, so here I was trying to be very generic. Yeah, this is not WIMP specific at all. Yeah. So I was at a conference right around the time I got my first faculty job here, and I was having dinner with one of the great esteemed men of the field, and he said, dark matter's boring. We're just going to find, it's some particle, we'll measure the mass, we'll give it a name, and we'll all go home. And my rebuttal was, well, that's probably too simple. Why shouldn't it be a new particle that has a whole new theoretical framework built up around it, right? If you have supersymmetry and you have a neutralino, you have all of supersymmetry to explore. If you have universal extra dimensions, that's a mind-blowing shift in how we think about the universe. It could be multiple things. They could be composite, right? If they're composite on an energy scale that's not probed by any of the evidence I gave you for dark matter, we can't tell. They could be bound by new forces of nature, and that would open interesting cans of worms. So you could imagine a discovery of dark matter exploding into a whole new field of dark sector physics. And I think the analogy here is you could have said several decades ago, neutrinos, they're boring. It's just a particle that goes through everything. There's nothing to talk about here. But if we hadn't understood neutrinos, we probably wouldn't have been as motivated to understand the weak nuclear force and a lot of physics that turned out to be quite important to us. So I want to flash back now to 2008 because there was a flurry of activity back then, a lot of anomalies that seemed to be pointed in the same direction of a new light particle that mixed with the photon, interacted in various ways. And some of these things have gone away and some haven't. It's just people got tired of talking about them. But there were a couple papers in 2008, one by Pospelov and Ritz, and then days later, one by Arkania Hamed et al. I was one of the et al. And those papers kind of opened the doors. Suddenly it was permissible to talk about new forces in the dark sector mediated by light particles, by which I mean tens of MeV up to a GeV. And there were 32 papers in the next 6 months, and those papers were some of the most cited particle physics papers in the entire year. So, and then, like I said, people kind of got tired and went on to other things. But let me just explain what happened back then. So there are many places to look. I forgot that was cheesy. Some of these have already been found. Let's go through the list here. Okay, so we have dark matter. We have, there was a satellite called Pamela that said there were too many positrons starting around 10 GeV and going up towards a couple hundred GeV. So those are measurements near Earth. There's also a balloon experiment called ATTIC that said there was too much E plus E minus. So here's Pamela. Here's the ratio of positrons over positron plus electron cosmic rays, right? 1, 10, 100 GeV. This is what's expected from, granted, a fairly naive model of positron production with collisions in the interstellar medium. And this is what you see. Don't worry about this so much. At these energies, the solar modulation of the 11-year cycle of the sun makes this flop up and down a factor of 2. So I'm not so worried that doesn't agree. But this is a violent disagreement here. There are people who have models of propagation that can try to make this turn up, but they require kind of wacky assumptions. So this makes it look like there's a new contribution of positrons with a steeply climbing spectrum here. If you look at the ATTIC data, it had a bump here, which has actually since gone away. AMS2 does not see that bump, and it has much better error bars. But at the time, we were wondering if we could kind of latch on to part of that bump too. Probably shouldn't have.
What's the y-axis there?
Sorry, this is just the number of electrons plus positrons, dNdE, times E cubed to make this somewhat flat. So it falls as about e to the minus 3.25. But in any case, to explain such things like that with Wimp annihilation, we need a much higher cross-section, right? We need a mass high enough, like TeV scale or a few TeV, that we can annihilate to positrons in that energy range. And then we need a cross-section a couple orders of magnitude higher than you would normally assume. But there's this idea called Sommerfeld Enhancements, where basically there's a new particle mediated a force. There's essentially an attractive force between Wimps, so they're much more likely to come together. They're even bound states, although they may never find themselves in the bound states, or like positronium, they might not stay there very long, and then they'll annihilate. But it's just the analog of gravitational focusing. And the only reason to show this plot is we get an enhancement to the cross-section that's 1 or 2 or 3 orders of magnitude, depending on where you are in some parameter space. But it's actually totally plausible to do this. So those were some anomalies near Earth that didn't make sense. Then looking towards the galactic center, there were some troubling things. There's the 511 keV excess, too many gamma rays, and too many microwaves, both of these with a hard spectrum. So in more detail, these are the excess microwaves seen by WMAP back 12 years ago or so. And this turned out to be related to the so-called Fermi bubbles, which appear to be coming from black hole activity in the center of the galaxy, blowing things out. So that turned out not to be part of this story. But this 511 keV thing, this is from a fairly old paper, but they've continued gathering data with the Integral spacecraft, this SPI instrument. And this has not gone away. There's something like 10 to the 43 positrons per second annihilating the center of the galaxy, and we don't know where they come from. I'll just say that again. We don't know where they come from. This has been a mystery for about 40 years. And, you know, several instruments, balloons, satellites have seen it, and, you know, people get tired of talking about it. There were suggestions that they come from low-mass X-ray binaries, but that's been pretty well debunked. So
Steady state flux. I just remember many years ago it seemed to be going on and off or something like that. Is that all gone away and it's now steady?
yeah, so many years ago there was a claim that it was fluctuating, but Integral has never seen a fluctuation, and it's much better data. Yeah. There is a new idea, actually. There's a class of supernovae that instead of making lots of nickel-56, goes in a different direction, you know, strontium, calcium, whatnot. And it's not that it makes more positrons per supernova, but because of the half-lives of the products in the chain, the positrons are created many decades later than they are in a normal type 1a supernova. And so there's these, you know, special kind of supernovae that may have very high positron escape fractions and maybe preferentially in the galactic center. That's the best explanation I've heard so far, but even that has a lot of question marks. So we still don't really know what's going on here. Here's a spectrum showing the line and the positronium continuum from the 3-photon decays. Okay, so without dwelling on that too much longer, the point here is there's something weird going on in the galactic center. I guess I noted on a different slide, you know, egret gave way to Fermi. We got much better gamma ray data starting in 2009, and Fermi's still going. And so even after studying the Fermi bubbles for years and trying to understand what's going on with that, even on top of that, there's still a gamma ray excess in the galactic center we don't understand. It may be a new population of objects, some version of millisecond pulsars. There's a lot of debate about this right now. It's probably not from dark matter, but, you know, things keep popping up in the galactic center. The more carefully we look, the more things there are. So that's been interesting. Here's another thing that just won't go away. The DAMA experiment, you know, sodium iodide crystals, looking at WIMPs scattering off of them, hopefully. And the idea is as the Earth goes around the sun, the rate of WIMPs hitting the detector changes. And so they see this annual modulation over many, many years. They did an upgrade to their instrument here, so you see much better error bars on these points than these points. But they're all consistent. And so they claimed, basically many years ago, claimed a high significance detection of something, but nobody believes it's dark matter, because any plausible theory that does this would be tested by the xenon experiments and, you know, many other things, and it just completely fails. So this has been a great mystery. You know, what is this signal? Where is it coming from? And in 2008, the idea pushed by Neil Weiner and others, including me, and actually this goes back to Smith and Weiner in 2001, is that if you have inelastic nuclear scattering, right, the assumption is always you have elastic nuclear scattering. WIMP comes in, hits an iodine or whatever, scatters it. But if it's inelastic, that helps. So first of all, there's a threshold energy to get over. So the tail of the velocity distribution is very important. And if you just work out the kinematics of that, the modulation of the signal through the year can be much larger than expected if you're only using the tail of the velocity distribution. Bigger nuclei are better. At that time, the data ruling this out were based on silicon and germanium, which are smaller nuclei. And if you've got this center of mass energy threshold to get over, you want to crash into a big nucleus. And just in general, high energies are better. So, so this was kind of pushing us in general thinking, in the direction of thinking, how do you make WIMPs scatter inelastically? So I'll come back to that. And then there's other things. I imagine there are people in the room who know way more about this than I do, but the mu on G-2 thing has been around for a long time. And, you know, sometimes things shift in the direction of theorists saying, oh, we weren't quite calculating it right, it's not as big a deal. And, oh, well, actually, no, it's still a big deal. So I don't know, that's just kind of out there. So then there are a lot of signals here. Some of them are wrong, and some of them are right, but have nothing to do with dark matter. Right? But if we take them seriously and try to build a model to explain them, then you know, any subset of these things that are right will still be explained. It's just kind of interesting to do the exercise. So we wrote this paper in 2008, which was not really a theory of dark matter, but a framework of thinking about these things in, where you've got Wimps, you've got a new light force carrier, it mixes with the photon. You can actually have Wimps scatter off each other inelastically, get excited and de-excite by emitting a virtual, you know, this new boson, a virtual boson, that then goes to E plus E minus if it's massive enough. Only has to be greater than an MeV. So that would explain the integral result. The inelasticity also occurs with nuclear scatterings, so then that gives you DAMA. Because of the photon mixing and the tendency to go to positrons, that happens not only in the, you know, in these scatterings where you're converting the Wimp kinetic energy to low energy positrons and electrons, but also in the annihilations, it likes to go to electrons and positrons at high energy, explaining Pamela. And so we were just trying to shoehorn all of this into one framework, and it actually works. There are regions in parameter space where you can explain all of those anomalies I listed with one new particle, basically. It's a new force of nature. It may seem extravagant, but if you can explain enough things, it's interesting. So, you know, just to review here, let me just skip to this. So which parts come from which experiments? So the high mass for the Wimp is required for these. If you're going to do this with kinetic energy, you need the center mass energy of scatterings to be over an MeV, so that implies a fairly massive Wimp. Ignore that, that went away. You need a large cross-section for things like this, so that implies the Sommerfeld enhancement, which again implies a new force mediator that has to be fairly light. The inelasticity is coming from DAMA and from this. Like I said, nobody believes this, but this is still there and never went away. And frankly, this never went away either, and it's 10 sigma, and I'd really like to know what it is. The tendency to go to leptons is coming from these, and that, you know, implies that this, whatever the Wimps are doing, they're leptophilic in some way if they're doing this. And then mixing with the photon is especially important for these, but actually it's important for many of them. So 931, so I should be moving on here. So we're led from all this to some new light state that could be a non-abelian vector boson, couples to dark matter, as a very weak kinetic mixing seemed to be the best way to do it with electromagnetism. And you know, we've overfit this. We've gone too far. But if any part of this is right, it would be interesting. So now,
Could you say again what the explanation is for the mu on G minus 2? Somehow I missed how you explain that.
I'm ducking that one because I don't know much about it, but there have been papers that claim that G minus 2 would be modified by the existence of a new particle that mixes with photons. So you have extra Feynman diagrams in there with some funny loops and things, and you end up changing G minus 2 by a small amount.
Do you know who's calculated that?
I can get that for you. I don't know offhand.
There was a paper by Marciano. Actually, he also couples to atomic phase well. It's kind of interesting. I have a slide on that.
Yeah, okay, good. So I think I basically already said these already. There's still a gamma ray excess we don't understand. Pamela was right. Dama's still there. Nobody believes it. These other things are still there and still somewhat confusing. And then we have a few newer things to worry about. So there's the proton radius problem, which particle bytes described as this. If you scatter electrons off of a proton, you know, you measure the size of the charge blob and you get 0.88 femtometers. but you get 0.84 if you scatter muons off of it. And so this appeared several years ago, as I'm sure you all know, and people said, yeah, maybe, do it again. And then they did it better, and it was still there. And now just recently they've done it with deuterium, and they find an anomaly with deuterium that's consistent with this. And what's kind of neat about that is Dave Tucker-Smith and Itai Yavin wrote this paper several years ago, motivated by this, that if you have new MEV scale force mediators, you can actually get this kind of an effect also. So that's something we don't have time to go into, but it's an interesting idea that that could be tied in. So until we understand the proton radius, I'd like to keep that in mind. And then just much more recently here, this is the beginning of this year, there was this paper on Beryllium-8, possible indication of a light neutral boson. The idea here is that you're making, so you've got Beryllium-8, which is unstable, right? But you can take a lithium-7, run a proton into it, make Beryllium-8 in an excited state, and see what happens before it falls apart. So they do this, and some small fraction of the time, well, I don't know that's that small, actually, you get internal pair creation. So you make a virtual photon that comes out, and you get a positron-electron pair in the nuclear de-excitation. And that's interesting because that vertex of virtual photon, E plus, E minus, we understand everything about that one. We're supposed to know how to do that, right? There are lots of things in particle physics that aren't fully understood, but that's supposed to be one of them. And so you can calculate the angular distribution of the electron-positron opening angle. And so you can calculate that and you can measure it. And the calculations are these solid lines, and the measurements are the crosses. So this is sort of tickling different states in Beryllium-8. And you see in some of the cases, you get this bump out here at 140-degree opening angle. Otherwise, everything fits the, quantum electrodynamics works. You predict what these are, and they just work. But there's something wrong, and this is 6.8 sigma. This is done by the ITAMP people in Hungary. So, okay, 6.8 sigma things come and go, but this is curious. And if you're willing to introduce, hypothesize a new light particle, again, now in the kind of 17 MeV range, and have, instead of going through a virtual photon, about 6^10⁻⁶ of the time you go through a virtual this thing, then you would get this curve. And it goes through the data points. If you change the mass either way by an MeV, it doesn't go through the points at all. So it's a pretty well-constrained mass for a particle that we don't know exists. So I was impressed by that. So just from the original experimental paper, they're saying mass of 16.7 MeV and branching ratio of 6^6. Such a boson might be a good candidate for the relatively light gauge boson or light mediator of the secluded Wimp dark matter scenario, or the dark Z, suggested for explaining muon anomalous magnetic moment. So that's, maybe a bit of a stretch, but it's really interesting to think in that direction. So I'm about out of time. There's a nice summary of the situation of this at the Particle Bytes website. This is, by the way, something that grew out of Astrobytes, which is a thing that started with the students in this building. And we're very proud of them for doing that to make astronomy articles accessible to the public. So Particle Bytes has done a pretty nice job of that too. And so at that link, they go through all the experimental evidence, a bunch of theoretical ideas, 4 or 5 different things that the new particle could be, and how there's something wrong with each of them. One idea is ruled out by the fact that you make pi zeros, and pi zeros often go to 2 gammas, or to E plus E minus occasionally. And once in a rare while, they should go to gamma and this new thing, if that mixing is really there. That's not observed. There are these particles like at Jefferson Lab in Virginia. They have a megawatt beam of high energy particles slamming into a beam stop continuously, and they look for things to come out the other side, and they put limits on the mixings and so on for such new things. There's some work at MIT with led by MIT on a free electron laser to do similar things. So there are lots of experiments going on right now looking for new light weakly coupled particles that mix with photons. None of them have found anything. They're starting to rule out an interesting fraction of the parameter space, but I'm just going to leave this there because I have no answers, and I'm not particularly an expert on this, but I'm very interested in the dark matter angle and whether the hints from the dark matter stuff have been pushing us in the direction of a new light mediator. And then with the proton radius of G-2 and beryllium 8 problems, and there are a couple other things that get kicked around too. I think it would just be amazing if the next big breakthrough in particle physics didn't come from LHC, but came from not exactly tabletop experiments, but modest-sized experiments that cost 10 to the minus 3 or 10 to the minus 2 of the LHC. Might be the thing that actually opens the new frontier, because that frontier might not be high mass, it might be weak coupling. So it's very important to keep that in mind. So thanks.
So on the beryllium 8 experiment, is anybody trying to repeat that?
I hope so.
Yeah.
So they've done it before. In fact, their first conference proceeding about this was 2008. So it's not an entirely new result. But so I think the claim was in this last round, this was already an nth iteration of trying to do this better and better. And there have been claims in the past about beryllium 8 that are wrong. And so in their paper, they're also debunking some previous claims. But those were not measured with this kind of significance. And they weren't such a nice bump that's fit by such a nice simple theory. They were more like, over a very broad range of angles, things aren't quite right, and it was just an experimental problem. But this is very fishy to just get a bump like that.
So is there something special about beryllium 8, or any nucleus with a 17 MeV resonance?
So it might be kind of an overlap of the energy of the resonance and the fact that there aren't that many nuclear states that decay by internal pair creation. I mean, yeah, I assume there are others that happen to have an internal pair creation at 17 MeV, but I don't offhand know. And so it might just be that that's the most convenient thing to use.
It's about the extra positrons in the middle of the galaxy. Are there extra positrons in the middle of other galaxies too?
We can't see, unfortunately. That's something that I talked to the integral team about years ago. Could we just stack, 1,000 nearby galaxies or something and see if we see positrons from them? And the signal to noise isn't quite there. It's too bad. It would be lovely to build a bigger, better positron, 511 kV telescope and answer that question.
All right, thank you
All right,
so much.
thanks.